Hey, Honors Physics, this is a new unit we're starting today, the kinematics of two-dimensional motion, aka projectiles. So let's brainstorm. What are some projectiles? Well, a cannonball being fired, a golf ball coming off a tee, a soccer ball being kicked, or even a football punted, but also dancers leaping on the stage, or a horse doing the same in equestrian sports. So lots of objects move in two-dimensional motion, and a lot of activities we do. In class, I often ask students to see if they can come up with one that's not mentioned. And some of the classic ones that are talked about are things like rockets, or even things like frisbees. And the reason why those are not projectiles is because we're going to find out that in projectile motion, there is only one force acting on the motion. And that only force that's allowed is gravity. And you might say, but the cannon blasts the cannonball. Once the cannonball has left the cannon, it is no longer under the force of that explosion, or the dancer is no longer pushing off on the floor once they are in the air. So let's go take a look at some of the preview of some of the words. You're going to notice that all the terminology is approximately the same, except we're going to be separating our motion into horizontal and vertical motion. And every problem is going to have both. The formulas for horizontal motion and vertical motion are almost the same as the ones that are on your equation card. Maybe they're written differently, but you should recognize those, and we will occasionally or down the road need some trigonometry. So here is the full definition. What is a projectile? It's any object that is in air or space that has been thrown or launched. Now, the word dropped, technically in some books, dropping an object makes it a projectile, but it does not obey the laws of projectile motion. So we're going to actually drop this. So a 1D projectile never curves. We've actually already mastered this. We called it free fall. So we're not going to revisit that. Sometimes it's called 1D projectile motion, but it's not needed. So for two-dimensional projectile motion, such as Angry Birds or so many video games where you're launching objects through the air, they create a curved path. And the name of that curved path is called a trajectory. And the shape of that trajectory is a parabola. So to turn that into an adjective, do you know that a parabola turned into an adjective is parabolic? So it's a parabolic trajectory. The top is called the apex of the flight, and that's something we've looked at in the past with vertical throws or motion in the vertical direction. So another word that we're going to introduce is when we measure the horizontal displacement. So we could use the old words, delta x, but when it comes to projectiles, we call this the range. The delta x, the horizontal displacement, is called the range. You know, they call it a shooting range. When you go to a driving range for golf, it means that you're hitting the ball horizontally some distance, but as it travels, it obviously also changes its height. And we're going to look at how those two motions are very different. So this is a little unfortunate. I think I've got a little glitch going on in some software that I've used for many years. This is called Explain Everything. And I can't rotate images or objects, used to be able to, quite freely. So we're going to turn sideways, and I'm going to just write it sideways, even though the video is vertical. That's going to be a little confusing. So let's start with the most basic projectile we can make. In fact, it's kind of boring. If we did this in person, you'd be like, what's the big deal? So imagine a ball that's rolling along at a constant velocity on a flat surface. And the moment it leaves the table, well, it starts falling. But it doesn't fall straight down, it curves. And there's our parabolic trajectory. And if we were to describe kind of the position of the object, and we were to map it out, do you notice that if the horizontal position is very consistent, that last one does not exist. Let's just undo it. The horizontal position, the delta x for each increment is the same, right? The horizontal progress And what that tells us, right, is that in the velocity in the horizontal direction, if the position is uniform, then the Vx is constant or uniform. So it has a velocity in the horizontal direction. In fact, we'd map that out. We'd kind of draw that in. We could show the velocity in the horizontal direction, and it would be the same, whatever the starting velocity was when it left the table. And we're going to start calling that Vx, the velocity in the horizontal direction. And it's uniform the whole time. Now, using another colored pencil, draw from the center of each object to the right-hand line of the grid. Basically, what we're going to do here is we're going to show that at 0 time, right, there, when it's still on the table, this is its height. Let's use another color. And then some unit of time later, 0.1 seconds, it's dropped a little tiny bit. And then another 0.1 seconds, it's dropped. And what do you notice about those positions? Well, that looks like the layout of a vertical free fall or an accelerated motion. So the horizontal motion is constant, but the vertical motion is constantly, right? It is a constant acceleration. Now, let's not get confused. Having a constant velocity and a constant acceleration are very different. In fact, right, one means you never speed up, and one means you're always speeding up. So if I were to now describe the velocities, at the moment it leaves the table, there is no vertical velocity. Think of it as the instant when it leaves the table, it hasn't had a chance to start falling. But after 0.1 seconds, it has started to gain a V in the Y direction, and then it gets a little bit larger, and then it gets a little bit larger, and then it gets a little bit larger still. And we now have, right, 2 velocities at every second, but they're very different. We have a 0 to begin with, and then it gets bigger and bigger and bigger all the way down. So to summarize, if we were to describe the horizontal motion, it has a constant velocity. Let's put in fact, a constant V. The acceleration is a big fat 0, right? Its value, the acceleration in the horizontal direction, it has none. We don't usually write that. We just say 0 doesn't exist. Okay, what's causing it? There are no horizontal forces. And you say, well, what about whoever pushed the ball when it rolled off the table? The push was before it became a projectile. During its flight in the air, there were no horizontal velocities. You might say, what about air resistance? And we're going to say it's negligible. It doesn't count. So if you were to plot the horizontal position versus time, you notice that they were basically going up, increasing in the forward direction by the same amount every unit of time, right? Very steady. The vertical motion has an accelerated motion, right? It's constant accelerated motion, and it has a negative acceleration. What's its value? Well, it's g, negative 9.8 meters per second squared. You could write that as a equals negative 9.8. And you don't know this yet because we haven't studied forces, but every acceleration is created by a force. And in this case, the force, right, equals gravity, the pull of the Earth. We're going to do most of our forces and problem solving on Earth. However, if you were to go to another planetary system, the moon, or to go to interplanetary space, you would have to do some educating of yourself to find out what the gravitational pull is. You're always being pulled by some object's gravity, maybe big, maybe small. And we've seen a graph like this in the past. We know this is a quadratic graph. And in this case, we're graphing Y position versus time. And it starts off at 0, like at the table height. And then it progressively gets more and more negative. Notice these values are actually, this is actually in the 4th quadrant. Here's 0, here's 0. And we're getting negative and more negative. And it's not by the same amount each time. And that's a hallmark of accelerated motion, right? So the delta y after 0.4 seconds is not a linear relationship to the delta y after 0.3 seconds. You can see it's increasing exponentially. So if you were to combine those, that kind of sounds weird, we could do separate calculations. We could predict exactly where an object's going to be in the forward direction, in the vertical direction, and the net result here is that if we were to time it and do the actual numbers, at 0 seconds you have 0y, that's right here. The horizontal motion, right, is also 0 meters. We haven't moved forward yet. Now, for this object, it's moving at 20 meters per second when it's launched. Its Vx is 20. So how far? 20 meters every second. So how far would it go in 1 second? Oh, it would go 20 meters forward. It would go another 20 meters forward after 2 seconds. Now this is weird. This is a graph that you've not seen. This is a delta y and a delta x plot. But if you read the fine print, it basically says, can you calculate? Well, in the horizontal direction, you don't really need to do much calculation because it's steady. It's going to gain 20 meters every second because it's not gaining speed, it's gaining meters. And that's how far out it would go. But vertically, if you were to start at the top, let's use red. You may not know this, but you can do a really quick calculation. Delta y equals 1/2 at squared because the v initial is 0. And so we would get delta y equals negative 4.9 times 1 second. Well, 1 second squared is 1, so you would drop negative 4.9 meters. So where is that on this scale? It's very small, right? It would be right about here, and it would be right about here. And then after 2 seconds, well, 2 seconds squared is 4. 4 times, can we just round that off? 4 times 5 is about 20. And then we would do 3 squared, 9 times 5. That's 45 meters, which is right about here. And then after 4 seconds squared, I'm doing this weird math kind of diagonally, that's 16. 16 times 5, well, maybe you can't do that one in your head. Let's just do it here, 30, 80 total. So now we're down to 80 meters. And let's see, and then 5 squared is 25 times 5, 5, 2, 10, 120. And what you get is that basically the ball is falling below its horizontal position, and we get a projectile. We get a parabola. So who lands first, though? I've got a question for you. I'm going to clean this up a little bit. Let's get rid of this. You know, you've already seen me do my noodling around to try to get those those displacements. In fact, I never wrote these in, right? So this was negative 20. Then what did we have? Negative 40. Nope. No, it was negative 45-ish. And then it was 80. And then it was 120. Okay, and the same would be true over here. We would have 0, negative 4.6, negative 20, negative 45, negative 80. You can put those in if you feel you want to. But this great question at the bottom, who lands first? The baseball that falls straight down, or any object that drops straight down, or the cannonball that starts from the same height above the ground and is launched horizontal. And I don't know if you've ever seen the Mythbusters episode. They did a famous one where a gun, a little pistol, fired a bullet horizontally, and they did it inside a building so they could kind of limit the amount of wind and air resistance. And they dropped a bullet at exactly the same time. And the question is, the bullet that curves and lands way down here, that was a huge building. I swear it was a half-mile long. Which bullet hits the ground first? The one that goes several hundred miles an hour forward, curves to the ground and hits the cement, or the one that's dropped? Do you think you know? The answer is they land at the same time. Gravity doesn't care. Gravity's not a person, so it can't care anyway, but gravity does not change how it affects objects, whether it's moving not at all and it just drops straight down, or if it's moving forward. Gravity affects it the same. And so what really controls your time in the air is what's your delta y? How much vertical drop distance do you have? And if they have the same delta y, then they will have the same t. And we're going to test that in class. I don't want you to take your word for it. I have a special device. It's like a gun, but it's like spring-loaded, and we'll take a look. Okay, so big summary, and bummer that it's sideways. Easy for Packet, but harder for you. So there are no horizontal forces. There is no horizontal acceleration, and the v is constant. Quick summary. The vertical motion, there is a force of gravity, and it's a vector, and it's downward. Therefore, there's an acceleration. G is negative 9.8 meters per second squared, always for all projectiles and any other object that's being affected by gravity. And it has an increasing negative velocity. It's increasing or changing. I will keep working to see if I can learn how to make things rotate. So at the bottom of this page, you're going to notice that this is the same as your equation card. You're going to need your equation card to try some sample problems that we're going to do next. Okay, let's skip this page. We'll come back. Hey, Honors Physics, Mr. Hausman here. We're going to take a look at number 2 on page 6, horizontal projectiles. So we started this one the other day. What we're talking about here is we have a situation where a cherry pit is moving along at a horizontal speed of 18 meters per second. And why is that relevant? Well, because if that object is moving along at 18 meters per second in a car and it's dropped, it's going to turn into a projectile that moves forward at 18 meters per second the entire time it's in the air. And that consistent horizontal velocity we call Vx. So the Vx is 18 meters per second. That's quite fast. Now, we don't know how far it lands ahead of the car. We don't know the delta x. That's called the range. And the range is actually the unknown. How far horizontally from the dropping point will the pit hit the ground? We don't know that. And you might get stuck because you're like, well, we also don't know time. So this is not a simple problem, just like we would have done in the past with horizontal motion. You know 2 variables, and you solve for a third. Instead, we're going to have to look at the vertical data. So what do we know about the vertical motion of a projectile? Well, if it is moving horizontal, completely horizontal, not up, not down, then its vertical velocity when it starts is 0. And we do not know the velocity when it hits the ground. We'll just leave that blank. But we do know that the acceleration is free fall. It's the gravitational acceleration of our planet. And we know that the delta y is negative 1 meter. Now, it doesn't say that, but you have to interpret that if it starts 1 meter above the ground, and then by the time it hits the ground below the car window, it is now negative 1 meter. That's important. It will not work out mathematically if you don't do that. And you might say, well, there's no way to continue this. But in fact, what's going on is that if you notice you have 3 given in the vertical side, then what you can do is you can use your kinematics formula to solve for t. Why t? Well, the reason is because time is in both sides. It's the same time. That is to say, the time to land out here is the same as the time to drop. So if we did a free fall drop problem and found the time to drop here, it's the same as the time it takes to land here. We did a demo in class and the marbles landed at the same time. I wasn't trying to, when we did that, emphasize that it's a lot different, but in many times when we've used high-speed cameras in the past, it's off by a little tiny bit, like a tenth or even less of a second. But sometimes it's not exactly the same due to air resistance. So let's go ahead and let's set up and think about what formula would we use to solve for t as our unknown. And I bet you can take out your equation card, do that now. And you're going to notice that you have a formula, delta y equals VIT plus 1/2 AT squared. It has delta y in it, it has v in it, v initial, it has t, and it has a. And your gut feeling may say that's quadratic if I'm solving for t. And in this case, because the v initial is 0, it's a little bit simpler. We just plug in -1 meter. V initial is 0, so that whole term cancels out. Half of -9.8 is -4.9. T squared. Divide both sides by -4.9. And t comes out to be, right, we have to first divide, and then we're going to square root. I'm going to do all those steps at the same time. So let's do that. Square root of 1.0 divided by 4.9. The two negatives cancel out. And you get a time of 0.452 seconds. Do we need all those decimals? Maybe we could stop at 0.45 because that's what the given had. But the reason why we carry another is that's not the final step. That's just step 1. Now we can use that 0.45 seconds, and the only formula that we have available to us for non-accelerated motion is velocity equals delta x over t. And now we can plug in our 18 meters per second equals a range, a delta x we do not know, but the time is 0.45 seconds. And when you cross multiply, you get 8.1 meters. Check that out, see if you get it. And that is how far the pit lands in front of its starting position, how far out. And the car probably kept up with it. So Lisa would look out the window, look at the cherry pit, think she's dropping it straight down. But anyone who's outside the car would see it move forward at 8.1 meters. Okay, let's do the bottom of 6. So the bottom of 6 is another similar scenario, but instead of Lisa Simpson, it's the Hulk, the big green Hulk. So he tosses a piece of granite. And I don't know how you throw things. Sometimes you throw it up at an angle. But in this case, we find out that he really pushes it forward. There's a horizontal velocity, and it's a piece of granite, so it's not moving that fast. Well, it is the Hulk. And it moves forward, curves, and in this case, he's throwing it out from the ledge of a cliff. What that really does is it allows us to have some drop, and then there's water at the bottom. And the question is, how far out? This is another exactly the same range problem. So let's go ahead and see how that works. We've got a Vx of 3.0 meters per second. We have a range we don't know. We have a time we do not know. We have a V initial of, say it with me, 0. The starting height for all projectiles that are launched horizontally is 0. You can count on that if it is a horizontal launch, if it's thrown sideways. Let's see, what else do we know? We know the acceleration is -9.8, always on planet Earth. And the delta y, I believe we know, is -10 meters. It's dropped 10 meters. And what's going to be our unknown? We're going to solve for t on the vertical. And the question is, do we always go from y to x? And the answer is no. If you knew 2 pieces of data on the horizontal side, then you might find yourself going the other direction. And I bet a lot of us can kind of foresee that happening. What you really need to have is your equation card out in front of you, and we're going to learn with a little bit of practice how to use any set of given to find any unknown or unknowns. So let's set this up. What did we do last time? We used delta y equals VIT plus 1/2 AT squared. We have the ease of canceling out VI because it's 0. And then we have -10 meters equals -4.9 T squared. This is going to become quite easy for you in a matter of maybe 2 practice problems. So let's go ahead and do that. Let's take the square root of 10 divided by 4.9. Now, if you notice that one of those is positive and you're therefore taking the square root of a negative, then what you've probably forgotten is you've forgotten one of these negatives. Projectiles always, that are thrown horizontal, always have negative displacements because they're curving downward. So you can't take the square root of a negative number, so those double negatives have to be there. And the answer I get is 1.43 seconds. I'm keeping an extra sig fig, an extra digit, because that's just step one. Let's go ahead now and use our horizontal motion. We've got Vx in the horizontal equals our range over our time. How fast it's going, we know is 3 meters per second sideways. We don't know the range, and we know it takes 1.43 seconds. So the velocity is slower than the cherry pit, but the time is greater. Let's see how this works out. What is 3 times 1.43? That's me just mistyping it on my calculator. Sorry for the delay. And I get 4.3 meters. Okay. These may seem pretty basic. They will get more challenging when we have multiple unknowns or when we have to be flexible and we have to go the other direction, time from the X to the Y. But so far, that's a good start. I'd like you to try the next few problems for a homework assignment. And whoa, jump in. So that's the final answer key to page 6, but you're going to watch video 2 to see how those are developed.